Hello, and welcome back. At the end of the last video, I asked you to either recall, discover, or look up in the textbook what this vector-valued function represents. So hopefully you did that, and you should have found that this represents a circle of radius a centered at the origin. Now, you might have looked that up, and maybe you even caught a glimpse of how we're able to determine that. Why does this give a circle of radius a centered at the origin? So remember, this is my x of t here. So this tells me the x component of my vector and the y component of my vector here. And remember that this vector-valued function, the curve that it generates comes from looking at the head of this vector at all possible t values, or t values within some domain. And so if this is the x component, the y component, the head of this is going to be at the point x of t, y of t. And what I can do here, notice what happens if I take x of t and I square it, and I add that to y of t squared. So x of t is a cosine t, so this is going to be a squared cosine squared of t plus b squared sine squared of t. B, where did the b come from? I have no idea. That's an a squared sine squared of t. If that were a b, then this would in general be an ellipse. And so I can pull that a squared out. I get a squared times cosine squared t plus sine squared t. And we know cosine squared plus sine squared, that's an identity we should be familiar with. That's just 1, right? Because this is on a circle of radius 1. And so we just get a squared out. So we have x of t plus y of t, or x of t squared plus y of t squared equal to a squared. And so the set of points satisfy x squared plus y squared equal to a squared, which we can recognize this set of points that satisfy this is a circle of radius a at the origin. So that's why this vector-valued function is on that the head of these vectors are all on a circle. That's the idea. So this is tracing out a circular path in the xy plane. Cool. This is going to be one useful tool for us, is to play around with the various components and see if they satisfy any equations that we can recognize as familiar geometric objects, especially in 3D. We might recognize that, say, the curve is on a hyperbolic paraboloid or a hyperboloid or something like this. So we'll want to play around with that and do this similar sort of analysis. Okay, so right, what is the difference between the vector-valued function? Why do we have a vector-valued function and also this other way to represent a circle, right? I could just say, consider this equation and know that it gives a circle of radius a. And now we have this other way for, you know, what's the reason that we have this other form to generate a circle? All right, what's the difference between a parametric equation and just an equation like this, the points that satisfy this, right? If they both turn out a circle, what's the point? Well, one important point is that these are vectors. R of t is turning out vectors. So if I plug in, say, t equals 0, so r of 0, let's just play around with this for a second. R of 0 would be a cosine of 0, so that's just a. Right, cosine of 0 is 1. And remember, we're working, we're going to start doing calculus in this, so go back to most of the time we're going to be using radians for our inputs of trigonometric functions. So this t value is in radians. And then sine of 0 is 0, so I just get 0 here. So I get the vector a0. I'll draw that here. a0, if this point is 0. I want 0a here. I want negative a0 here. I want 0, negative a here. Of course, if I plug in something like r of pi over 2, what do I get here? Now, cosine of pi over 2 is 0, and sine of pi over 2 is 1, so I just get a out, and that gives me the vector here. So that was a big time jump. I also could have done, say, r of, let's do r of like pi over 4. Then cosine is root 2 over 2, so this would be a root 2 over 2 for the x component, and a root 2 over 2 sine of pi over 4 is also root 2 over 2 for the y component. And so I would get a vector, looks something like, beyond this circle, something here would be, this would represent, or this vector would be r of pi over 4. This vector here, right, is r of 0. And here we have r of pi over 2. Right, so I can keep doing this. Right over here will be, what, r of pi. And down here would be, what, r of 3 pi over 2. And it gets back to here, and it keeps going. And so this is tracing out the circle with a certain orientation to it. So I'm going to, I'll do this in red, the actual circle that it's tracing out. Again, it's not going to look exactly like a circle. It is a circle, theoretically, but I'm not the best drawer, and I didn't keep everything exactly. So it traces out the circle, and it'll keep going. And most importantly here, as I increased the t value, we went around the circle in this direction. So this curve, this circle, has an orientation to it when I think of it like a vector-valued function. So that's a really important point, is that these have orientation. As t increases, how is the curve traced out? So in this case, we're going counterclockwise, or a positive rotation about the origin here. Whereas with the set of points, if I'm just considering the circle, right, a, negative a, negative. If I'm just thinking of the set of points that satisfy x squared plus y squared equal 1, all I just get is this set of points. There's no direction to it. That means when I find, say, the tangent line at some point, so we're going to think about tangent lines. Right, remember doing that? We take derivatives of all parts of this, say derivative with respect to x. I don't know if you remember doing this in Calc 1 or doing some of this in Calc 2, right? We would get, if I apply dx to both sides of this equation, right, I'll end up with 2x plus 2y dy dx equals 0. I can solve this thing and figure out what my slope is at every x and y value. Right, remember implicit differentiation. I can find the slopes at any point, and then I can form tangent lines. So say at this point, I could plug in that x and y value and recover what dy dx is. In this case, it'll be 0, and we get a tangent line here at a, right? We would end up with a tangent line here at a. And notice this is a tangent line. It sort of goes in both directions. Or if I did it over here, if we draw a tangent line, it goes in both directions like this. Or if I did a tangent line over here, right, again, it goes in both directions. We're talking about tangent lines for this set of points. Over here, when we have an orientation to it, well, if I want to find, say, the tangent here, I get more than just a tangent line going in both directions, but rather a tangent vector that's telling me the direction it's traveling at that point. So when I take a derivative of this vector-valued function and then plug in pi over 2 for t, what's going to come out is this vector here. So it's tangent to the position vector, right? They're 90 degrees to each other, so they're orthogonal to each other. That's going to be important. And it's tangent to the curve as well. And it has a direction to it. So here, our object is actually moving downward. Here, it's moving to the right. So we're getting more information than just the set of points. We're really recovering how this thing is moving through space, whereas here, things are sort of static. Over here, they're dynamic. And that's the idea. So that's the big difference between these two. I've already sort of hinted at some calculus that's going to happen. I can't wait to get into that, but a couple more preliminary things before we can begin that. So I'll see you in the next video. We'll keep talking about our vector-valued functions. We'll look at some examples of some more difficult ones than just circles. Hope to see you there.